more examples to understand how the convolution sum can be evaluated both graphically and analytically. So this is example 2.3 from the course text, and it says consider an input sequence x of n and a unit impulse response u of n, okay, indicated by h of n. So you have this sequence, both are infinite length sequence, so that means both sequences are starting from n greater than or equal to 0 because they have u of n's, okay. So alpha is indicated as a positive real fraction whose magnitude is less than 1. So you see the trend is, since alpha is less than 1, then with the positive powers of n, you have a decreasing trend, okay, so it's a decreasing exponential sequence sort of. So for example, the first value is 1, then you have alpha, okay, since magnitude of alpha is less than 1. The second sample is alpha squared, third, so so on and so forth, okay. So first is 1, then it's alpha squared, for n equal to 2, for n equal to 3, this is alpha cube, and this thing continues. So you can say that this sequence, also this sequence is a bounded sequence, okay. You can say that this sequence is a bounded input. So since we are using convolution to understand how the output is being evaluated, so since we due to convolution, it implies that the system is also linear time invariant. Now if it leads to a bounded output, then there is there's a third qualification besides linearity and time invariance that should be associated. So we have to find out that if this is stable or not. So whether it is LTIS, okay. So if a bounded input leads to a bounded output, then that's a criteria of stability of the system. Okay, now we know that the input is bounded, so x of n has the maximum bound for all n, and that bound is unity. Okay, the magnitude of xn is less than equal to 1 for all n. That means it's a bounded sequence. Okay, all right. H of n is the unit step function. Okay, so it starts with 0 and goes to infinity. Now, so also to help us visualizing and calculating the convolution sum of the signals. In figure 2.6, we have depicted the signals xk for the following h minus k. So we have the flipped version of h of n, and then we have h minus 1 minus k, that is one shift towards left, then one shift towards right. That is you have hn minus k for 3 values of n. So this is the flipped version of h of n, okay, flipped version of unit step signal, n equal to 0, and then you have this shifted by n equal to minus 1, n equal to plus 1. Okay, so we have these three sequences depicted in figure 2.6. Okay, and then finally there's another sequence. This is hn minus k for an arbitrary positive value of n and an arbitrary negative value of n. So there are 5 sequences. This is figure 2.6. Okay, this is figure 2.6. So this shows a graphical interpretation of the calculation of convolution sum, for example 2.3. So you have the sequence, and the sequence is a function of k. Okay, so this xk is my alpha k uk, and then I have the flipped version of the unit step function. This is my unit step function h of n, which is the impulse response of the system, and this is flipped as a function of k. This is flipped over here. This is h minus k, which implies n is 0. Okay, n is 0. Now if you recall, the convolution output, or the convolution sum of the LTI system is given as a function of k. It's given as x of k into h of n minus k. So it's the product of two sequences, and then it involves the summation as well. So there are basic 3 operations. First is you have flipped this, you shift the sequence, multiply it with xk, and then sum it over all the values of the k. Okay, over all the samples over k indices. Okay, so to evaluate at n equal to 0, this is xk h minus k. To evaluate y of n at n minus 1, you need h minus 1 minus k. Now one thing you notice over here is that if you look at this graph, h minus 1 minus k has no overlapping sample with regards to xk. This implies also, just look at over here. This is the last figure for n less than 0 for negative indices. There is no overlapping or no non-zero sample that overlaps with x of k. Therefore, this product is 0. This product is 0 for n less than 0. Okay, that means your y of n, or the output of the system, is 0 for n less than 0. Okay, so we are not going to consider y of n for n less than 0. Now, where do we have the overlap? For example, let's consider this. This is for n equal to 1. Okay, this is for n equal to 1. And you see that there is an overlap. So the multiplication of these two, if you might want to do this analytically by hand, then y of 1 is my summation, convolution over k, summation is over k. So this is xk h of 1 minus k. Okay, and if you do the multiplication sample by sample basis, looking at this graph, and for this graph for n equal to 1, so you see there are only two samples. Okay, so for example, this sample is 1, this is alpha, so my y of 1 is simply 1 plus alpha. Okay. Similarly, if you have to do this for n equal to, for some quantity n greater than 0, okay, it could be 2, 3, or whatever it is, then hn minus k and xk, this for y of n, okay, and y of n will be equals to summation over k. Now you see your hn minus k is 1. Okay, so all the samples are 1. So all the samples are 1. Xk is given by alpha k. So this I can replace by alpha k, right? And my lower limit for k is supposed to start from 0. So I don't need to consider the negative values of k. So this starts from 0, and then the upper limit is n. The sample that is overlapping up, the overlapping is between 0 to n. Okay, this is the region where the samples are overlapping. So I need to consider this upper limit as n. Now if you expand this expression, you have this as 1 plus alpha squared plus alpha cubed. Okay, where alpha is a real positive fraction, and this thing continues. Okay, this trend continues, and you notice that this is nothing but a geometric progression. Okay, so this is a geometric progression, therefore its sum can be written by a geometric progression formulation. That is, the common ratio is, you see, is alpha. So this is 1 minus alpha. How many number of terms? From 0 to n, this is n plus 1 terms. So let's have this as n plus 1. Then 1 minus alpha. Okay, this is for n greater than 0. You see, if you have to evaluate this expression, okay, now I have y of n, okay, for n, or you can put it like this, for n greater than or equal to 0. Now if I have to check for y1, for example, can we have this expression from here? You see, for n equal to 1, this becomes 1 minus alpha squared, or 1 minus alpha. So you see, this 1 minus alpha squared can be written as 1 minus alpha, 1 plus alpha. So this is 1 plus alpha. Okay, so I have my y of n. Either I can write this as n greater than or equal to 0, or I can have this as u of n. Okay, so both are have the same interpretations. So you see, you can do this either graphically, or you can do this analytically. If you have the description of this input sequences. So the other way of looking at this process is, what you're doing is you're sliding the shifted version of the flipped impulse sequence through the input sequence xk, right? So for example, this is sliding over here. So this sequence slides to the right, and then you multiply the samples, add them up, and you have the convolution sum result. Okay, so that's your output that you're looking for. Now the question was, if you recall, whether the system is stable or not. So at the limit, because this sliding can continue forever, because this is a unit step function, what happens, the question is, what happens if I say that, okay, goes to, n becomes infinitely large, n goes to infinity. Now, since alpha is a fraction, okay, it could be half, one third, or whatever it is. That means your y of n as a limit will approach to uh, this thing in the numerator, alpha n plus 1 will become 0. So this y of n will approach to 1 over 1 minus alpha, which means that your output is bounded. Okay, this is for n approaching to infinity, which means your output is bounded, therefore your system is stable. System is stable. This is both, this is actually, there are three properties associated with the system. The first is that it's linear, then it is time invariant, okay, which leads us to evaluating the output by convolution sum. And then, yes, it does, a bounded input does lead to a bounded output. I mean, the bounded input was bounded by 1, by unity, if you recall. And my output is bounded by 1 over 1 minus alpha. That means my both inputs and outputs, input to the system and the output to the system are both bounded. Therefore, the system is stable. The system is stable. Okay. All right. Now, from this figure, okay, so this is about 2.6 again. So from figure 2.6, we note that for n less than 0, there is no overlap. So this is describing what is happening over here. So what we saw was that this, for n less than 0, there was no overlap. So there's no need to evaluating for n minus 1 or n minus 2 over here. So the first thing you must notice is that there's no overlap between non-zero points in xk and hn minus k. Therefore, for n less than 0, your product is 0. xk, hn minus k is 0 for all values of k. Hence, from the following equation, from this equation, we can say that y of n is 0 for n less than 0. Then, for n greater than or equal to 0, we have the expression, okay, because xk is alpha k, that is how it is defined. And but we usually define this in terms of another dummy variable k, let's say. So this becomes alpha k, which has to vary up until n. Okay, this overlap is up until n. This is n. Okay, so this is from k equal to 0 up until n, and then we sum it up. Then we have to sum it up. So this is alpha k, and your final expression is given by the geometric progression sum, which is 1 minus alpha n plus 1 minus alpha. You see the total number of terms are n plus 1. It starts with 0, and this is up until n. So if you include 0 as well, then this becomes n plus 1. So y of n is 1 minus alpha n plus 1 over 1 minus alpha u of n. Now this is y of n is sketched in figure 2.7, and you notice that as n is progressing, becomes progressively large, your output is bounded by 1 over 1 minus alpha. Okay, so this is a stable system.